Um, Hello all. So we'll be presenting our paper today. So our paper is 2DFQ, which is two-dimensional fair queuing for multi-tenant cloud services. Um, and so the presenters are me, Arvind Kalyan. My teammates are Prajay Patil and Varun Rahul. So yeah, we'll just move on with the introduction part. So, like, we'll just take a scenario where we imagine a busy highway where vehicles of all sizes compete for space, small cars, trucks, and buses. Now, imagine if only the largest vehicles were allowed to pass first, leaving the smaller cars stuck for hours. This is exactly what happens in multi-tenant cloud systems with traditional schedulers. In these environments, resources are shared among multiple tenants with highly variable workloads, but current scheduling algorithms such as weighted fair queuing fail to handle workloads with unpredictable costs and large variability effectively. This results in unfair resource allocation, bursty scheduling, and significant latency spikes for smaller tenants. As cloud systems scales and workloads become increasingly dynamic, the need for fair and efficient resource management becomes critical. To address this, the authors have proposed two-dimensional fair queuing, a novel scheduling algorithm that improves fairness and efficiency by distributing requests intelligently across threads and handling unpredictable workloads effectively. In this presentation, we will explore the challenges of traditional schedulers, introduce 2DFQ and its extension 2DFQE, and demonstrate how they address burstiness and unpredictability while improving performance and fairness in multi-tenant environments. So, yeah. So, in this slide, as you can see that uh, we have a iceberg kind of image where the high execution concurrency in shared thread pools complicates fair resource allocation. Variable request costs spanning up to four orders of magnitude lead to scheduling inefficiencies. Unknown and unpredictable request costs make cost estimation challenging and error prone. Burstiness in traditional fair scheduling algorithms like WFQ and WF2Q causes latency spikes for small tenants. Yeah, so here in this slide, it highlights the key motivations during the development of the two-dimensional fair queuing algorithm. One of the primary goals is to achieve fair resource allocation in multi-tenant cloud systems, ensuring that all tenants receive a fair share of resources. This prevents aggressive or poorly behaved tenants from monopolizing resources, which cloud otherwise lead to the starvation of other tenants. Additionally, the algorithm aims to minimize burstiness in scheduling by addressing the delays caused when small requests are blocked by larger ones under traditional schedulers. By reducing such burstiness, the system ensures smoother and more predictable performance for all tenants. Another critical motivation is the ability to handle the highly variable request costs, as multi-tenant systems often experience workloads with wide variances in request sizes and unpredictability, spanning up to four orders of magnitude. The algorithm is designed to manage the variability effectively while maintaining fairness and efficiency. Furthermore, ensuring smooth service for all the tenants is a core focus, providing consistent and predictable performance even in environments with competing large or unpredictable workloads. This is essential for maintaining tenant satisfaction and meeting service level agreements. And also here, this slide underscores the importance of resource isolation, which is vital for preventing high latencies um, or even system-wide outages caused by poorly written or aggressive workloads. Lastly, the slide emphasizes the need to support high concurrency, which is a hallmark of modern cloud systems. With tens to hundreds of requests being processed concurrently, the algorithm addresses the challenges of distributing resources fairly and efficiently, ensuring the system operates smoothly even under heavy loads. So all these motivations collectively highlight the need for advanced scheduling mechanisms like 2DFQ to handle the demands of multi-tenant cloud environments. So yeah, so as you can see here, this image here illustrates weighted fair queuing, where incoming packets are classified into separate flows, each assigned a weighted share of resources. The scheduler processes packets based on their assisted assigned weights, ensuring fair resource distribution across multiple flows while maintaining order within each flow. And also, this method is particularly effective in multi-tenant environments where multiple users or processes with varying resource requirements share the same infrastructure. By ensuring that no single flow dominates the system and all the other flows are served in proportion to their assigned weights, WFQ provides a balanced and predictable scheduling mechanism that aligns with the principles of fair resource management in cloud systems. And in this image, as you can see that the it illustrates the difference between bursty and smooth scheduling in a multi-tenant systems. In the bursty schedule, the image A, a large request from tenants C and D dominate, causing significant delays for smaller requests from tenants A and B. This uneven resource allocation needs to be it needs to be unpredictable and inconsistent performance, particularly for smaller tenants, a common limitation of traditional scheduling algorithms where larger requests monopolize resources. And in the second image, the smooth schedule, it shows a more balanced approach where requests from all tenants A, B, C, and D are interleaved fairly. Smaller and larger requests are processed side by side, ensuring predictable and consistent performance. This fair distribution of resources avoids monopolization and delays, creating a balanced and efficient system. So, such a smooth scheduling is achieved using the 2DFQ algorithm by addressing burstiness. 2DFQ ensures equitable resource sharing among tenants, providing fairness, efficiency, and predictability, even in environments with high concurrency and variable workloads. And in this, as you can see that this slide emphasizes the critical need for fine-grained resources isolation in shared system like Hadoop distributed file system (HDFS). In such environments, poorly written map-reduced jobs can act as distributed denial of service attacks by consuming disproportionate resources, leading to delays or failures for other tasks. To address these issues, uh, HDFS introduced priority queuing, which ensures that high priority jobs such as critical or time sensitive processes receive adequate resources, while lower priority tasks are managed more effectively. This example illustrates the importance of sophisticated resource management mechanisms to maintain fairness and prevent resource monopolization in shared systems. Our research builds on these concepts by proposing a more robust framework that ensures fair and predictable resource allocation even under dynamic and predictable workloads. As you can see here there are two key motivations for the proposed scheduling approach. The first one is the work conservation, ensures that all worker threads remain fully utilized by continuously processing requests from per tenant queues, maximizing system efficiency. And the second one, the non-bursty servicing, it emphasizes smooth and fair distribution of resources among tenants, avoiding scenarios where extended periods are dominated by a single tenant's request. And also, this approach ensures predictable and equitable service for all tenants, addressing fairness and performance concerns in multi-tenant environments. Here, the graph highlights the critical challenge faced in multi-tenant cloud environments, the inverse relationship between quality of service, that is the QoS, and the unpredictability in cost variation. As the unpredictability of workloads and cost variability increase, the quality of service decreases sharply, as illustrated here. It is illustrated by the downward trend of the curve here. And the traditional fair scheduling algorithms such as WFQ and WF square Q struggle to maintain high QoS in the presence of highly unpredictable workloads. This is a significant issue because these unpredictable workloads represent typical real world scenarios in cloud systems. The inability of existing algorithms to address this problem underscores the need for a more robust and advanced scheduling mechanism that can effectively manage high levels of unpredictability while ensuring consistent and fair QoS for all tenants. So here we explain the key concept of 2DFQ, a novel scheduling algorithm designed to address fairness and burstiness challenges in multi-tenant cloud systems. Here, the multi-tenant environments often experience issue with the traditional schedulers like WFQ and WF square Q, which allow larger or unpredictable requests to dominate resources. Here, the 2DFQ resolves this by distributing requests across multiple threads, ensuring that no single tenant can monopolize resources and creating a more balanced and equitable scheduling process. In addition to its core functionality, the algorithm is further enhanced through the 2DFQE extension, which introduces cost estimation mechanisms to handle workloads with unknown or highly variable request costs. By using cost estimation, the 2DFQE ensures fairness for all tenants, preventing unpredictable or aggressive workloads from impacting predictable tenants. This feature is particularly important in dynamic cloud environments where workloads can vary significantly both in size and frequency. The impact of implementing 2DFQ and 2DFQE is profound. These algorithms improve resource isolation, ensuring that each tenant receives its fair share of resources without interference from others. They also enable smooth scheduling, reducing latency spikes, and ensuring consistent performance for all tenants. Furthermore, 2DFQ significantly enhances latency and fairness in highly concurrent environments. Again, as we saw about making it a more robust solution for modern cloud systems. Here, the image here illustrates the core concept of 2DFQ, a scheduling algorithm to handle multiple tenants, so which share a which are resources in a cloud system. Here, tenants A, B, C, D represent different users or processes competing for resources within the same shared environment. These requests are processed by worker threads such as WO and W1. In traditional systems, larger requests from tenants like C and D can block smaller requests from tenants A and B, causing delays and inefficiencies. 2DFQ addresses these challenges by optimizing the distribution of requests across threads, as shown in the diagram. Uh, Smaller requests like A1 and B1 are smoothly interleaved with larger ones like C1 and D1, ensuring that no single tenant monopolizes resources. This approach minimizes delay, maintains fairness, and provides predictable performance for all tenants, even in environments with diverse and highly variable workloads. And also here we can see that the image here explains the start and finish times of requests as managed by the weighted fair queuing, that is the WFQ and its variation WF square queue. The requests from tenants A, B, and C and D are processed with different start and finish times based on their sizes and priorities. For tenants A and B, which submit smaller requests, the processing times are closely spaced as their requests require resource allocation. In contrast, tenants C and D submitting larger requests have longer intervals between start and finish times, reflecting the larger resource demands of these requests. While WFQ and WF square queue ensure all the other requests are serviced, the bursty scheduling caused by simultaneous handling of large requests C and D can lead to delays for smaller tenants A and B. So here this visualization highlights the need for a more balanced approach like 2DFQ to ensure smoother and fairer distribution of resources across all tenants, regardless the size of their requests. Yeah, so my colleague will take over now.
So let's dive deeper into the schedules for WFQ and WF square Q. This is the slide which is basically illustrating the request schedules for both of these and how they are executed, associated with the real world execution. Now, the key observations here can be, for instance, like the larger tenants like C and D tend to dominate the schedule, and this generally causes to have significant request sizes, and this causes smaller tenants like A and B to have longer wait periods, and this results into unfairness. WF square Q tries to mitigate this by considering finish times more dynamically. However, it still prioritizes a tenant for an extended period before switching to others, and this still leads to a bursty behavior. Now, the burstiness causes inconsistent performances and long latencies for smaller tenants, for those with which are frequent and small requests. Over time, this can somehow degrade the overall system and the performance of the tenants. Uh, so we can see that both WFQ and WF square Q fail to balance the scheduling needs of diverse tenants effectively, especially when there is a high variability in the request sizes. Next slide, please. So this is the modified eligibility times. And here you can see the key observations are like unlike WFQ and WF square Q, where all requests are elevated for scheduling simultaneously. 2DFQ staggers eligibility time across threads. Now, what this effectively does is it ensures that smaller requests like A1, A2, A3 in this case are eligible more sooner, and thereby they are processed without being blocked by larger ones. This approach prevents any single thread from being overwhelmed and overcrowded, and this thereby leads to a smoother schedules, and the latency spikes in this case are much smaller compared to the previous cases. We can also see there's a formula provided here, which is for eligibility. And the formula is used to calculate the request's eligibility by adjusting its start time and its cost dependent factor. This adjustment ensures that requests which have smaller costs, like A1, A2, are prioritized earlier, and thus creating a much fairer, what to say, a much fairer transition. Um, Next slide. Yes, we can see there's the request schedule for 2DFQ, which is what the paper is mainly about, uh, and how it improves scheduling fairness efficiency compared to its predecessors, which are WFQ and WF square Q. We can see that requests for smaller tenants like A and B are interleaved, and for those like tenant C and D. This ensures that, again, as discussed before, the smaller tenants A and B are not blocked for extended periods of time. Unlike in WF square Q, where tenant D might monopolize and dominate the scheduling queue and thus lead to latency, which can affect to the entire system all along. This interleaving, which is occurring in 2DFQ, not only reduces the burstiness but also ensures that all tenants receive a fair share of resources regardless of their request size. The result is a system that's not only fairer but also more efficient, as it minimizes delays and improves overall thought output. Next slide. Now, this is how we are going to address high request cost variability. This slide majorly focuses on challenges of high request cost variability, a common issue in systems like Azure Storage. In the left, you can see the graph illustrates a wide range of requests costs for different APIs. You can see some APIs, such as API A, consistently require very small resources, while others, APIs like API G, requires a lot of costs and vary up to four orders of magnitude compared to A. And in the right side, you can see cost variability across tenants. While tenants consistently issue small requests, other mix large and small requests, creating unpredictable workloads. Now, how does this impact the scheduling? High variability in request cost makes it challenging for traditional schedulers to provide fairness and consistent performance in the system. So we can say that 2DFQ addresses this variability by spreading these requests across various threads and using cost-aware eligibility adjustments, ensuring smooth and predictable schedules as compared to bursty and latency-prone schedules. Next. Uh, Now there are a lot of unknown costs, which unknown request costs, which need to be addressed. And one of the most significant challenges in multi-tenant systems is handling these unknown request costs. The traditional algorithms like WF square Q and WFQ struggle with unknown costs. They often underestimate these requests, and this thereby leads to blocking of resource contention. Now, what 2DFQ's approach is, it's a pessimistic estimation, which is 2DFQ assumes unknown requests may have high costs. So it is better prepared than traditional systems like WFQ and WFQ, F square Q. Thus, they ensure monopolizing resources. This conservative approach prevents delays for other tenants. And the other approach is retroactive charging. Once the request completes 2DFQ, adjust resources accounting based on the actual cost, maintaining fairness over time. Now, the overall outcome is that these two mechanisms ensure that unknown requests are handled effectively and help minimize the impact on overall system. Um, in this slide, we can see three graphs, and we are going to mainly discuss addressing unknown requests cost. In graph A, we can see there's a stable tenant. This graph represents a stable tenant which with consistent request rates and cost over time. Such predictable behavior makes scheduling very straightforward. In graph B, we can see a tenant whose request costs change gradually over time. Although this is less predictable than graph A, this change in remain manageable as there's nothing drastic in it. But in terms of graph 3, it illustrates a very unstable tenant which has very frequent cost changes, and you can see these changes are really abrupt. This level of unpredictability complicates scheduling, often resulting in the latency spikes and problems like unfair resource allocation. These variations demonstrate effectively why traditional scheduling algorithms like WFQ fail to maintain fairness and efficiency in real world systems because real world systems tend to be more similar to Graph C. Next slide. Now, handling unknown requests with 2DFQE. This, as talked earlier, pessimistic cost estimation and retroactive charging are the two ways which help it effectively manage this. Now, unknown requests are conservatively estimated as a high cost to prevent them from monopolizing resources or delaying other tenants is pessimistic cost estimation. While retroactive charging is the same, its requests are complete. The actual cost is compared to the estimated cost, and then the adjustments are made retroactively, which is later after the process is complete to ensure fairness and correct resources uses. These mechanisms ensure fairness and can go past very unstable tenant systems like Graph C. Here's a small illustration which shows you how it's effectively managed. And the flowchart is like a timeline to visually explain how interaction occurs between, pessimistic estimation and retroactive charging. Um, Another issue is handling unknown requests with 2DFQ is stabilizing service rates. Overestimation when costs are unpredictable, overestimating ensures that a request doesn't dominate resources if the actual cost is underestimated. 2DFQE uses real-time feedback to dynamically refine scheduling priorities, reducing variations in latency and service rates. The outcome of this is the mechanisms enable consistent performance even under highly unpredictable workloads. Thus, by stabilizing service rates, 2DFQE ensures that tenants experience predictable and reliable performances. Next slide. Now, to enhance predictability and fairness, DFQE's innovative mechanisms enhance system predictability and fairness even in presence of unknown variable request costs. This is majorly done by segregating unpredictable tenants from predictable ones. 2D FQE ensures that smaller, consistent tenants aren't penalized. Uh, Also, the retroactive adjustments further ensure that resource allocations align with actual usage, maintaining fairness across tenants. The outcome of this is that the approach results in, again, a more equitable distribution of resources and predictable performance for all tenants, regardless of their request patterns and sizes. These improvements basically make 2D FQE a more robust solution for addressing these challenges, enhancing more on the fairness and predictability of the cloud services. Next slide, please. Again, we can see there are a lot of illustrations, and let's go over a few important ones. Like for the box plot on the left, We can see sure that the 99 percentile latencies across various schedulers, 2DFQ achieves significantly lower latencies compared to traditional systems like WFQ and WF square Q, thus indicating a much smoother and predictable scheduling for real-world systems. And on the right, we can see there are scatter plots. The scatter plots effectively illustrate the service rates for tenants. With 2DFQ, the rates are more consistent and closely aligned with fair allocations, and this effectively reduces the variability in the system. The results validate the effectiveness of 2DFQ and DFQE, demonstrating their superiority in terms of fairness, latency, and predictability. So the authors, with their novel approach, were successfully able to eliminate the burstiness and the inconsistencies and the latencies which were occurring in the earlier and traditional systems like WFQ and WF square Q. Now over to my teammate Varun.
Uh, Today I'll be presenting on the 2D FQ and 2D FQE scheduling algorithms and their significance in multi-tenant cloud environments. We will explore how these algorithms outperform traditional schedulers in fairness, efficiency, and scalability. Additionally, I'll share detailed metrics, challenges, and solutions and discuss their real-world applications. Uh, Let's start by comparing the 2DFQ and DFQE with traditional scheduling algorithms. Traditional schedulers like WFQ and WF square Q often face challenges such as burstiness, which leads to uneven resource distribution and poor performance consistency. In contrast, 2DFQ and DFQE reduce burstiness, ensuring more consistent service rates across tenants. Data shows that these algorithms significantly outperform traditional schedulers, reducing variations in service rates and improving latencies. These improvements are critical for multi-tenant environments where fairness and performance predictability are paramount. Next slide. Now let's see the benefits of 2DFQ and multi-tenant environments. The first key advantage is predictability performance. By minimizing variability in service rates, 2DFQ ensures stable system behavior, which directly enhances tenant satisfaction and system reliability. Another critical benefit is scalability. 2DFQ is designed to scale effectively, ensuring fair resource allocation even as the number of tenants or workload demands increase. Together, these benefits make 2DFQ a highly effective solution for managing shared resource in multi-tenant environments. Next slide. Now let's see at how 2DFQ is implemented. This algorithm is designed with a modular architecture. This allows it to integrate seamlessly into existing cloud systems without requiring major changes to infrastructure. It also uses advanced cost estimate techniques, which analyze historical data and monitor runtime metrics to dynamically adjust priorities. These features ensure that the scheduler optimizes resource allocation in real time, improving both efficiency and fairness. Next slide. Implementing 2DFQ poses several challenges, but the solutions developed make it a robust and practical algorithm. One challenge was handling the unpredictable nature of the service request in cloud environments. To address this, 2DFQ includes an adaptive scheduling mechanism that dynamically adjusts to changing workloads, ensuring fair resource distribution. Another challenge was preventing the algorithm from becoming a bottleneck by employing optimized data structures and efficient algorithms. We minimized computational overhead, allowing 2DFQ to deliver high performance without straining the system. Next slide. This slide highlights the performance of 2DFQ in terms of service lag reduction. The cumulative distribution shows the service lag standard deviation across tenants. The red curve for 2DFQ demonstrates significantly lower variability, proving its abilities to stabilize performance even for tenants with small predictable requests. The box plots compare service lag across WFQ, WF square Q, and 2DFQ. Notice how 2DFQ consistently maintains narrow distributions, indicating lower oscillations and higher fairness. These metrics demonstrate how 2DFQ delivers predictability and consistent performance. Next slide. This slide provides a detailed analysis of service lag metrics across tenants, focusing on the consistency and fairness provided by 2DFQ comparing to WFQ and WF square Q. On the left graph, we see the cumulative distribution function of service lag standard deviation across all tenants. The red line represents 2DFQ showing significantly lower deviation compared to WFQ and WF square Q. This indicates that 2DFQ reduces service lag variability effectively, especially for tenants with small predictable requests. On the right box plots, they compare the distribution of service lag experienced by individual tenants, T1 to T7. For WFQ and WF square Q, we observe wider distributions, indicating more variability and oscillations in service lag. In contrast, 2DFQ's distribution is narrower and more stable, with fewer oscillations, even under dynamic conditions. This comparison highlights 2DFQ's ability to maintain consistent service lag and fairness across tenants, even as workloads fluctuate. It depends on predictability performance, which is crucial for multi-tenant environments. Next slide. This slide focuses on how 2DFQ performs under increasingly unpredictable workloads. On the left graph, it shows the service received by tenant T1 under different scenarios, 0%, 33%, and 66% unpredictability. 2DFQE, represented by the red line, consistently delivers stable service levels even as unpredictability increases, while WFQE and WF2QE uh, exhibit more fluctuations. On the right heat maps, it visualized thread occupancy. As workload unpredictability increases, 2DFQE effectively isolates small, predictable requests. This slide focuses on 2DFQE performs under increasingly unpredictable workloads. Uh, the graph shows service received by tenant T1 under different scenarios, 0%, 33%, and 66% unpredictability. 2D FQE, represented by the red line, consistently delivers stable service levels even as unpredictability increases, while WFQE and WF square QE exhibit more fluctuations. The heat map visualizes thread occupancy. As workload unpredictability increases, 2D FQE effectively isolates small, predictable requests and balances larger, more complex ones, maintaining fairness and efficiency. This demonstrates 2D FQE's robustness in managing complex workloads. Next slide. This slide provides a detailed look at latency and service lag metrics under different workload scenarios. The latency distributions for tenants under 0%, 33%, and 66% unpredictable workloads show that 2D FQE consistently provides the lowest latency for predictable tenants like T1 while fairly managing larger workloads. The CDF graphs confirm that 2DFQE minimizes service lag availability even under highly unpredictable conditions. The latency box plots for fixed cost tenants further emphasize 2DFQE's ability to prioritize small, predictable requests and maintain efficiency. The results highlight the algorithm's ability to handle unpredictable workloads while ensuring fairness. Next slide. Looking ahead, the success of 2DFQE and 2DFQE opens up exciting possibilities for future research. One area is further optimization of the algorithm to adapt to increasingly complex and diverse cloud workloads. This could only include fine tuning its cost estimation techniques or enhancing its scalability. Another potential direction is integrating machine learning to predict workload patterns and make even more intelligent scheduling decisions. This would allow the algorithm to anticipate demand and allocate resources proactively, improving efficiency even further. These advancements will make 2DFQ even more valuable as cloud environments evolve. Next slide. To conclude, 2DFQE and 2DFQA present a significant leap forward in cloud scheduling. Their ability to reduce service availability, maintain fairness, and scale effectively makes them ideal solutions for modern multi-tenant environments. The metrics and evaluations we have seen today demonstrate their real-world impact and highlight their potential for future innovations. Uh, and from this paper, we have learned sections on motivation, design, implementation, and evaluation, the use of diagrams, real world data enhanced understandings, the limitations of existing scheduling algorithms in multi tenant cloud systems, the value of separating requests by cost and using adaptive mechanisms like pessimistic estimation, practical insights into improving fairness and efficiency in high concurrency environments. And with this, we conclude our presentation. Thank you.